Think engineering is just equations or blueprints? Think again. From mind-blowing tech to game-changing innovations, All Things Engineering by EIT brings you real stories, real people, and real impact. Your front row seat to the future of engineering.
Hello and welcome to this podcast, Engineering at Scale, Asset Integrity and Complex Challenges in Global Megaprojects. Hello everyone, I'm Arti Siddhpura, an on-campus lecturer and course coordinator at EIT. I look after mechanical engineering courses as well as safety, risk and reliability courses. I manage accreditation, content updates, lecturer allocation, and ensure that industry and student feedback drives continuous improvement. So today we are exploring asset integrity and the complex challenges engineers face in global mega projects that impact economies, communities, and safety on a massive scale. We will look at how performance and reliability are maintained and what lessons help new engineers thrive. And joining me is Allison Selman, an industry expert with hands-on experience in asset integrity across major projects. Allison, could you introduce yourself?
Thanks, Arti, and thank you so much for inviting me to do this podcast. I'm very excited. So my name is Allison Selman. I'm the Managing Director of Atris, a subsea and pipeline engineering consultancy. I'm also the Business Manager for Asset Integrity and Decommissioning. My volunteer role is actually I'm WA President of Engineers Australia this year. So I have over 25 years of experience in mining and offshore oil and gas industries. I've worked on quite a few projects now, from small projects through to mega projects in Australia, Indonesia and Thailand. But one of my biggest observations is, regardless of the size of the project, the size of the operation, asset integrity is absolutely critical for the project and for the operations. So my core area of expertise spans integrity management strategies, risk management, inspection, monitoring, maintenance plans, and decommissioning of primarily subsea and pipeline infrastructure.
Thanks, Allison. That breadth of experience across different regions and asset types really sets the scene for today's discussion. Well, I'm not executing mega projects directly. My focus is preparing engineers to excel in them. In our program, we emphasize safety, risk, and reliability, the pillars of asset integrity. In our bachelor's and master's program, we emphasize a lot on job safety analysis. We do have workshop activities, hands-on activities, and students must complete a job safety analysis before starting any such activities. So this builds a habit of identifying hazards, assessing risks, and implementing controls, skills that translate directly to large-scale projects. For postgraduate students in graduate diploma of engineering and graduate certificate in engineering, mainly focusing on safety, risk, and reliability, we also go deeper into core pillars of asset integrity and risk management. I would elaborate a little bit more about the units and content we cover under these two courses. So we cover system safety and risk management. So this introduces hazard analysis, risk assessment methodologies, and safety management systems integrated into the life cycle. Another unit is incident investigation and learning from disasters. And in this particular one, students analyze major industrial accidents using structured models like ICAM, XIMAP, etc. to understand root cause and systemic failures. We also have functional safety and safety instrumented systems aligned with IEC standards 61508, 61511, and that includes HAZOP, LOPA, SIL determination, and SIS lifecycle management. We do reliability engineering and data analytics as well, and that's where we cover reliability prediction, fault tree analysis, maintainability, and statistical methods. And then we also have focus on human factor and process safety. I will elaborate this a little bit later in the podcast. And we also have a capstone project that culminates all this knowledge and skills into one final project. So these units, we try to make them align as much as possible with international standards like IEC and relevant ISO standards. And also we embed reliability best practices and assessments also mirror those industry workflows. We do have quizzes, case studies, we do have project reports, etc. So Alison, from your vantage point, where does asset integrity start on a mega project, and how early should teams think about it?
Very good question, Arti. So in my experience, asset integrity should start in the concept and design phase with a really, really clear understanding of the performance standards that are required for the asset, which in turn defines the requirements for choosing the right material, defining each component's criticality, requirements for integrity management, and the inspection, monitoring, and maintenance strategies needed to achieve the desired performance. Now, many operators leave it till too late. Unfortunately, if you leave integrity management planning to the operations phase, you are losing the opportunity to actually design out the risk for the most effective way to control the hazards. Now, the hierarchy of controls for eliminating hazards there are 6 levels. The first one is to eliminate the hazard, where you physically remove the hazard from actually happening. You can also substitute where the hazard is replaced with a safer option. You can also isolate, and this is where you isolate the hazard from the surrounding people and the environment. Number 4 is engineering controls, where you start reducing exposure, so the hazard is present, but when it happens, you reduce exposure by implementing the physical safeguards around it. Or administration controls, where you're reducing exposure by implementing procedures. They're less safe than engineering controls because obviously procedures can be missed or not followed correctly. And then the final level of control is number 6 is personal protective equipment. Now, there's always a cost-benefit trade-off between the technical solution and additional controls and the benefits it will provide. So what this means is we can eliminate the risk altogether, but it might be too costly to do so. Real life. So for example, let's use an example of a subsea carbon steel pipeline that's transporting highly corrosive product from an offshore platform to an onshore plant, and let's see how the 6 controls can be implemented. So number 1, eliminating. The cause of the hazard is actually the corrosive fluid. So to eliminate the situation where the fluid is corrosive, you can build a processing plant offshore to process the product and make it non-corrosive for transport in the pipeline. But obviously, that's a really, really high cost. Secondly, substitution. So you can make the pipeline itself more corrosion resistant by replacing the carbon steel material with a CRA material or a lining. But again, this comes at a very high cost. So other controls that you can use, isolating. So pipelines come with isolations at either end, at the start and at the end. And what happens is if there's an issue, we are able to contain the fluid within the pipeline so it doesn't impact people or the environment. In terms of engineering controls, you can do things like implement a high corrosion allowance or thicker wall pipe so that we understand the hazard is there. We know that corrosion will occur, but because we have sufficient meat in the pipeline, that we won't have a loss of containment or failure event. Administrative controls. So these are procedures that you can implement, such as chemical treatments or inspection and monitoring to check on how corrosion is progressing in the pipeline, and you can respond appropriately. And PPE, in this case, probably not much use if we're also offshore, because you wouldn't be having the right PPE because the pipeline's underwater. So doing this at the design stage has a lot of value. In one of my projects, we found by going through this risk assessment project a potential hazard with the riser, which is a vertical section of the pipeline that connects to the platform. Now, what we found was that the riser could not be accessed during operations, and because of this, there's no way of actually inspecting the riser and to check on its condition during operations. But because this was picked up during the design phase, the designers were able to redesign the riser arrangement, and then during operations, they could actually inspect the riser. So there's a lot of benefits if you start early.
Yeah, that's a really practical example of how risk decisions made during design can dramatically reduce reliance on operational controls later. And it echoes the mindset we try to build early in engineering education as well. So talking about a bit more about technical complexity in mega projects. Mega projects stack complexity, multidisciplinary interfaces, global supply chains, diverse regulations, and extreme operating conditions. The mindset that helps is system thinking plus disciplined risk practice, in my opinion. So just giving a couple more examples of how we embed that in our courses. So we have introduction to system safety, risk management, and reliability, very introductory unit that sets the stage for the students who don't have that sort of background. So in that particular unit, we build that discipline really early. We build it through risk and hazard analysis from first principles, and later the full toolkit. We equip them with HAZOP, Bowtie, FTA, RCA, and job safety analysis. And then we also embed safety management systems in the system lifecycle that includes safety, governance, and culture. We also expand the lens in human environment and workplace health and safety. We cover occupational hazards, human factor integration, and crisis and emergency preparedness. That's crucial in mega projects where people, process, and environment they all intersect at the same point. So Allison, could you share a technical challenge from a mega project and what made it complex and how your team structured the risk analysis and approvals?
Absolutely, Arti. And I totally agree with what you said around the complexity of mega projects and how starting with a systems thinking way and applying structured risk practices is absolutely what's needed. So mega projects are complex in nature purely due to the size and the volume of the asset infrastructure that is involved. Adopting a systems thinking is also understanding that from end to end, any operation and any asset is very complex. So there's always a mix of mechanical disciplines, civil disciplines, chemical disciplines, and all those act and interact together to create a successful asset. Now, a structured risk analysis relies on a well-formed framework that comprehensively documents each critical component in a systemic way and applies the risk assessment framework to objectively and systemically run through all possible scenarios and hazards that can occur through the different phases of the asset life cycle. Now, many people don't realize this, but asset integrity can actually be impacted from the fabrication stage. For example, if the fabrication is not done correctly, if there's the wrong materials, or if the fabrication is out of spec, that has implications further along the track. Same with transport and installation. Quite a lot of issues, for example, occurs because a lot of our mega infrastructure, like the platforms and the FPL, so they're actually manufactured overseas, all the way in Korea or wherever it is, and then very slowly transported by barge to the Northwest Shelf or the Bass Strait. And during that transport and installation phase, a lot can actually happen to our asset to impact its condition. Commissioning. Again, you might think that is quite a simple step, but a lot of things can go wrong during the commissioning phase, where you can impact onto how the asset is handed over to operations. And you can actually damage the asset during commissioning as well. And operations. So operations is actually the longest phase of any asset, and nowadays with good engineering design, we're looking at 20, 30, sometimes 40 years of design life or more. So depending on also the stage of the project, the reason we're assessing, doing a risk assessment, there's actually quite a number of risk assessment tools with different purposes that we use throughout the design and process. So for example, you can do a HAZOP, which is a hazard and operability study. Now, HAZOP is used to examine the impact of deviations from design intent, often using guide words like no, more, or less applied to process parameters such as flow, pressure, and temperature. Now, what HAZOPs try to do is like, what happens if we deviate from normal operations? What happens to the asset? Then you can also do a bow tie analysis, which is more a visual risk assessment tool that maps out how threats cause an event and the consequences that eventuate from this event. It also shows potential accident scenarios, identify weakness in the controls that we have implemented, engineering or administrative, or maybe we don't have enough controls in place. And then it helps us communicate the risks to other people as well. You mentioned fault tree analysis. That's absolutely, again, another very, very valuable tool. So fault tree analysis is like a top-down method that maps out how component failures and human errors combine through logic gates, as in an AND and OR, to cause a major system failure, which is the top event. It helps safety engineers understand complex failure pathways, identify root causes, quantify failure probabilities, and prioritize mitigation actions to improve system reliability and compliance. Finally, I'll talk about RBIs, or risk-based inspection assessments, which is the bread and butter of what I do. So RBIs are a strategic engineering method that prioritizes equipment inspections based on the actual risk of failure, which is rather than, sorry. Okay, Rob, we're gonna edit that. I'm coughing, and we'll start at RBI again, sorry. Okay. So finally, I'll talk about RBIs, or risk-based inspection assessments. Now, these are a strategic engineering method that prioritizes equipment inspection based on the actual risk of failure rather than fixed or prescribed schedules. So what we do there is we analyze the probability or the likelihood of failure and the consequence of failure, be it safety, environment, or economic, to come up with an overall risk ranking to optimize resource allocation, improve safety, and ensure asset integrity, especially in high-risk industries like oil and gas. So the fundamental theory there is that if we have X amount of dollars to spend on inspection and maintenance, which we always do because nobody ever has like an unlimited budget. Where do you want to spend that money? Right? It's the same like how you're budgeting in your household. Absolutely, you have X amount of dollars to, as extra income in a year. You always prioritize your mortgage, you prioritize, your bills. And then if you have a leftover, do you prioritize a holiday or that new sofa? So it's the same kind of idea where everyone has limited resources. So we want to prioritize it to address areas where we have the highest risk to our operation. So there's lots of many other tools, which I'm sure Arti will teach you in your course. Fundamentally, what's important is that you learn to understand what tool to use and when and why it's important.
Absolutely. So that's a great illustration of how early and structured analysis prevents cascading issues later on, something we repeatedly reinforce throughout this real failure case studies that we teach our students. Now, as we are talking about mega projects also come with larger teams. So at scale, maintaining integrity throughout the large teams, I consider that as a bigger challenge. And also, in my opinion, integrity is both a system as well as a culture. Asset registers and criticality, inspection and monitoring strategies, permit to work, and disciplined management of change. So just a couple more examples of how we teach those sort of things. In our process safety unit, students walk the safety life cycle from hazard recognition and toxic release modeling to layer of protections and operating and permit procedures. In safety systems, tools and method unit, we get hands-on with functional safety. We follow IEC relevant standards, also has open LOPA, SIL determination, SIS configuration, and performance evaluation. And as I keep mentioning, GSR 512 is our capstone project where students put together all the knowledge and skill, as well as a lot of students are already working in the industry and they have a lot of experience as well. So they put that experience in that capstone project, and they plan and manage their projects like real world engineering initiatives. They develop timelines, identify risks, apply structured methodologies to deliver the final outcomes. So, Allison, how have you structured integrity management across big teams? What tools and techniques help keep operations, maintenance, and projects genuinely aligned?
Thanks, Arti, and great question. You are correct that in mega projects there are lots of teams and lots of people involved, and lots of different people have come with a different level of understanding of asset and how to manage an asset. So the foundation for a structured integrity management program is defining very clearly from the start a component hierarchy and also the risk assessments that have been performed. So each asset will have to establish and build a computerized maintenance management system, or CMMS for short. There are quite a few different systems or tools that are available. The most common tool that I used are like SAP PM and Maximo. So these systems are used to resource, plan, and document activities like inspection, monitoring, and maintenance and repair that is performed against each task throughout its asset operating life cycle. Now, setting up CMMS is usually done at the design phase because it's quite a task. At a high level, you first have to define the component hierarchy and what they call the lowest level of maintainable item. So are we going to build maintenance programs to the level of, for example, I'll stick with pipeline as an example, to the level of a pipeline? Or do we want to go down to the level of a flange or a bolt or a gasket? So the more levels that you build, the more complex the system is. So again, there's a balance between the level of detail and the practicality of it. So even if you build like a system for gaskets, you can ask yourself, are you realistically going to do any regular inspection or maintenance tasks on a gasket, or will you wait till you have a failure to respond? So you need to think about the setup. Then one of the challenges also, given the fact that these assets, as I say, now operate for 20, 30, 40 years, which will outlive any single person's career. One of the challenges with working in this space is also a lot of information gets lost. So it's absolutely critical, especially if you're in a mega project where information is everywhere, there's a ton of information, that we not only collate the information, but we collect the correct information and we put it somewhere where we can easily reference and pull it up when we need it. Things like drawings or reports are super important. Next step is then to set up your inspection, monitoring, and maintenance tasks according to the specifications or the risk assessments that have been done by integrity engineers or the maintenance engineers. And once these are set up in the CMMS, how the operators use it is they can then see what work they have to do in this year, next year, 3 years, and kind of plan ahead in terms of resources, whether it be money or the right people doing the job. And then within each system, there's also like an approvals process. So making sure that the right people are actually reviewing and approving and updating information in the system is really, really critical. So the CMMS itself is the core, one of the core maintenance management systems. Now, in any mega project, there are many other systems that are used to manage the asset. So the CMMS is often linked with other platforms like an asset integrity management platform, an inspection manager which collects and maps all the inspection outcomes, laboratory information management systems, or an ongoing or live risk registers. So there's lots of different systems that link back to the CMMS. Now, each of these different systems also collect different types of information. And because, again, once you hit operations, there's so much data that's going to come back, especially nowadays, and we're going to talk about data in a sec. But the volume of data that's coming back now, it can be overwhelming. So what we tend to do is we set up integrity operating windows, which is like triggers, limits that we use to sort of screen the data that's coming in. And once we exceed these limits, it triggers a more detailed review to check whether the system or the asset is performing as we expect. So the engineer is also usually responsible for setting and reporting against key performance indicators, KPIs, which is a way of monitoring whether the system is performing as expected by our design. Now, in offshore oil and gas, which is where I work, because of the high-risk situation, each operator sets their KPIs, and then the regulator, whether it's state or Commonwealth regulator, they actually come and audit the operator quite frequently to see whether the operator is meeting their own KPI. So it's very, very important that we understand that. Another very key process is management of change, or people call it MOC for short. We like our abbreviations, which is the process that's specific to how we manage and control change that happens to our process. So MOC is initiated when a change is needed, and instead of going out and then making the change, what we want is a systemic approach that then defines the need for the change that will be performed, and more importantly, then you sit down as a team to assess the impact of the change to make sure that there will be no adverse effects or what other cascading impacts that may have on other aspects of your operation. And then importantly as well is to document the approvals that has been made for the change and the justifications and the why. And finally, when the change is made, to close out the change when it's been implemented. So a lot of the times, one of the problems we see quite often is something's changed in the system, but the relevant documents or drawings haven't been updated. And what you have then is future engineers working on incorrect information, which then becomes quite a risk to any operation. So documentation is absolutely critical, given, as I said, any asset is probably going to outlast any engineer. Having like transparent document that's accurate is absolutely critical for any operation.
Great. Thank you, Allison, for sharing that holistic overview. I really like that emphasis on governance and traceability. It's exactly the kind of systems-based thinking we try to cultivate, so engineers understand that integrity outlives any one individual. I would just repeat that. Let's change our focus a little bit slightly on the lessons learned. So students usually ask where the deepest learning happens. And my answer is at the boundary between plan and reality. So to put it into practice and to equip the students with the right skills, we have this particular unit, which I really love. It's incident and accident investigation and learning from disasters. So it's more about structured learning. Methods like ICAM, XIMAP, Taproot, STAMP, SERA, and other detailed, etc. are used. They are equipped with those methods, and then they are given those detailed cases, and we walk them through the case analysis like Piper Alpha, Flixborough, Bhopal, Fukushima, all those cases. And we connect that to reliability practice in another unit, which is reliability engineering, where FTA, FRACAS, accelerated testing, human reliability, maintainability, and availability, all those skills are taught, and also assessments are there that require analysis and recommendations. So Allison, could you share a time when things didn't go to plan? How you separated symptoms from causes, and what process or design changes stuck as a result?
Absolutely, Arti. It's so important to understand what's happened before so that we don't repeat the same mistakes again. As they say, once bitten, twice shy, and third time you're a fool. Lessons learned and documenting the process of lessons learned is another way of documenting the successes and the failures of any project. What worked well, what failed, and how we could or we should do things differently next time. Lessons learned can occur at any time. It can come specifically as part of the end of the project, as part of the closeout process. It can come from individual subject matter experts who have delivered on similar projects before, or it could come during the project, with especially when you talk about mega projects. there are multiple phases of any mega project. They always talk about phase 1, phase 2, phase 3. But so learning from phase 1, applying it from phase 2, and so forth, can happen like that as well. So things never go to plan. I've never seen a project that has ever gone to plan in my 25 years. So there are different ways of doing things. So even though things don't go to plan, sometimes the consequences are minimal. So you learn and then you move on and say, don't do that again. However, when things don't go to plan and a big failure occurs, usually, especially in our industries nowadays, the work usually stops. There is a very, very increased focus, which is great, on process safety in our industries. And because of that, because of, examples like Piper Alpha, as you said. So work usually stops, and then we do a root cause analysis, especially if the event has led to something undesirable. And usually the two big triggers are if someone got injured, or we have created harm to the environment, or cultural heritage. Those are the big triggers right now in Australia. So we need to understand what's happened, why it's happened, and how we can prevent it from happening again. So once we've done that, and once we put the right controls in place, then usually we're happy and we're confident that we can continue with the work as planned. So it's good and well to do all this root cause analysis and then, work it out within your project team. But more importantly, when we get the opportunity, is also to make sure that, as industry lifelong learning, that we share our knowledge and we share the lessons that we learn to others within the organization and the industry, so everyone can benefit also from lessons learned or what happened. Sometimes it can be quite sensitive and quite challenging to do it while a project is still live, but whenever there's an opportunity, fundamentally engineers should try to educate and help each other. Usually on a project, we document lessons learned into a couple of ways. So one common way is to capture it into a register, which then people look up in future projects to use. Or if it's something that is occurring systematically, generally we can also look at establishing a new procedure or updating a new engineering standard to make sure that it becomes a standard organization-wide to control future hazards.
Thank you for sharing those really powerful points, Allison. We also teach students that documenting lessons learned isn't just compliance. It's a feedback loop that drives reliability and safety culture forward. So let's talk about emerging technologies and improving outcomes. We are seeing integrity shift from reactive to predictive and proactive, as you have already mentioned. The industry is now focusing more on becoming more proactive. So in our case, we have a couple of units where we teach data analysis and statistics for reliability engineering. So that builds the data backbone, probability and statistics, Weibull analysis, EMSA, QSUM, confidence intervals, all sorts of skills and tools. And students apply those tools in case study and final project reports as well. They turn raw data into maintenance and inspection priorities. And then in reliability engineering, it ties analytics to practice, accelerated test analysis, proportional hazards modeling, PHM of repairable systems, and design for maintainability. And finally, capstone project is where students integrate technology with context, building a research-backed solution. So, Alison, what technology has genuinely moved the needle for asset integrity in your projects? And what data governance made it effective rather than noisy?
Thank you for the question, Arti. Now, this is the most exciting part, I think, of asset integrity, reliability, risk management. In my 25 years of working in the industry, this has been the biggest change. So technology has so much greatly improved our ability to manage our assets. It has moved the needle on so many aspects, in particular for where I work in offshore infrastructure, where a lot of the times my assets are in the ocean. So it's difficult to access, it's quite challenging, and it's quite an expensive integrity management regime. Now with technology, everything's faster, everything's cheaper, everything's so much easier, and the quality of data we're getting back is amazing. One of the most exciting changes, I think, has come with developing effective and efficient 3D imaging technology and software. So historically, engineers managed with 2D drawings. I remember I went up to do this survey, and even before 2D drawings, the operator handed me like a pack of blueprints. So even for me, that was eye-opening. The evolution of 3D imaging also allows us to better visualize our assets, better plan and document our asset management practices and findings. We can collect so much high resolution, high volume data quickly now with new technologies such as drone, LiDAR, which is a laser system, acoustic surveys, and much more. So I think humans are very visual animals, and when we can see something, we can understand things so much better and so much quicker. So one that's been a boom, and it's now pretty cost effective. The other big area of improvement I've seen is sensors. Same the phone, where we've gone from a hand phone, a phone exchange, to a phone, to a brick as a mobile phone, to these teeny tiny things we keep in our pockets as smartphones, and they're like mini computers now, and they pretty much run our life. So sensor technology is the same. The sensors have become incredibly smaller. They've become more accurate. So what that means is it allows us to do more. It allows us to see more. It allows us to collect more data. And when we have all that, we can actually make sense of what's going on with our asset a lot better. So along with all this technology is the tools and the digital tools that have enabled engineers to also execute complex analysis of the data that is coming back. So my one advice is buyer beware. While it's nice to have all these shiny new toys, returning all this data and returning, all this volume of information is great, but also make sure you understand what data you're collecting and why, because a lot of the times I've observed the data being collected, but either it's not being analyzed, so why you bother collecting this data in the first place? And the second thing that I notice is there's no understanding of whether the data coming back is sensible or not. So you need to understand what data you're collecting, why, and whether it's sensible. Coming with all this data then, as we said, is an incredibly large volume. data governance is becoming more and more important in the modern world. So in terms of also understanding what data is being collected, how it's being returned, we need to also specify how it will be stored, how it will be processed, what's normal, what's not. Do we have the right tools to analyze the data when it comes back in that format? And how are we going to apply this data to manage our assets? So in sometimes more data is not necessarily the right answer, but the right data and why we're collecting it should be what we're targeting. So a very good example is on one of the more recent projects. We have a dynamic flexible system, and it got specified, this amazing fiber optic system which runs through the riser to collect, pressures, temperatures, stresses. Amazing technology and amazing new way of what they're intending to do with the data. And then reality struck, right? They were like, oh, this system is going to return 1 gigabyte of data per day, per 24 hours. What's the cost? And how are we going to collect and store that data over 40 years? That's a lot of gigabytes. And all this data is coming, this 1 gigabyte of data each day is coming back as raw data. So what is the software tool that's going to take that data and create that into some kind of information or trend or something that will make sense to an engineer? So that's one of the more recent examples, I think, that more data is great, but then we need to understand what we do with it next.
Yeah, thanks, Allison. That's a great reminder that technology only adds value when engineers are clear about purpose, data quality, and how insights will actually be used. So, yeah, thank you for sharing that. Now, moving on towards almost the closer of the podcast, let's share some advice for students and young engineers. So, I'll go first. My advice for them is build holistic capability, technical depth plus risk literacy, systems thinking, and communication. Learn to quantify uncertainty, justify trade-offs, and document decisions clearly. Based on what discussions we have, I can also share 3 habits that can help in complex projects. So the first one I would say is ask crisp questions. Clarify scope, constraints, and failure consequences. If you are not sure about anything, please don't hesitate in terms of asking questions to get more clarification. Second is make risk visible. Use simple criticality and consequence of failure framing. And third habit that they can develop is close the loop. Write short post-action notes so lessons stick. So that's from my end. Allison, what would you tell new engineers joining a mega project team?
Absolutely. Very good advice, Arti, and absolutely agree with all the points that you raised. For me, one of the benefits for engineers is, as I say, we're visual animals. So if you ever get the opportunity, always get on site. Number one, get close to the assets, get close to the people, whatever it is, walk the plant, walk the operation, read the history, shadow the people that actually work there. Don't be arrogant. So one of the things is, these operators or these technicians, they have worked there for a long time. They know the asset inside and out. And just because they don't have an engineering degree doesn't mean they're not smarter than you. So learn from the people who are, on the face of the operation. Learn the standards and the tools that your team uses. So we talked a lot about the different tools that are available, but every operation and every operator also have their own ways of doing things. And so it might be quite different when you go from one to the other. So don't assume that what you know, don't make the assumption that what you learn from one operator is the right way and not the other operator. There's always lots of different ways to do the same thing. Practice evidence-based escalation. Bring data, bring knowledge, bring objectivity, and don't bring subjectivity to solve an engineering problem. Be open and listen to more experienced engineers who also have lots of knowledge to share. And throughout your life and your career, be curious about learning. So even though I'm 25 years in the industry, I'm still going for training and development. I'm still reading. I'm still going to lunch and learns, because there will be an endless amount. Nobody will ever know everything. So the biggest success you have is always to be curious about learning. And I think the other question you asked me was, as an employer, what do I look for in a graduate? Number one is communication. So the ability to speak and write clearly and concisely is key to having success. Now, most engineers go, but if I can do all this programming and I can do all this whatever, which is great, absolutely essential. But if you can't communicate the work that you've done, why you've done it, and especially to the client or to your boss, then it will be a roadblock. Number two, technical. So engineering is a technical field, and the marketplace right now is highly competitive, and grades do matter. So not all employees are looking for like the top 100% or the top performers, but generally grades are reflection that you've worked hard and that you've understood the technical content, and then you have managed to successfully complete your exercise or your exam, which is a task. So that's how it translates into the hiring process. Personal. So engineering is always a team sport, and individuals who have demonstrated some kind of team involvement during their student years, so where you can participate in student associations, volunteering, sporting teams, internships, or anything that involves you working with a team, will be looked on more favorably than someone who's just prefers to fly solo and all they do is focus on their academics. Another very important skill is problem solving and critical thinking. I know it sounds contradictory to what I just said about engineering being a team sport, but it's more the critical thinking. So to be able to be given a task and analyze the problem and work through a solution, and have the sort of critical understanding that yes, that answer kind of feels right, or not, that's not incorrect, or I need to find out more. So the ability to question yourself and what you're delivering is also very, very important. And finally, as we said, we are moving into the realm of technology, AI, and all that. So digital literacy is a must. While not all jobs require data analysis, AI familiarity, or programming, most engineering roles will involve the high use of digital tools in one way or form. Every organization and every operation is different. Basically, for calculating, drafting, presenting, reporting, those are fundamental. And then for high-end engineering or analytical jobs, then you need to have a good understanding of analytics, AI, programming. Python is becoming used a lot in many engineering industries.
Thank you. That's excellent advice, Allison, especially the balance between technical strength, communication, and curiosity, which really determines how quickly young engineers grow in complex environments. So, Megaprojects succeed when engineering excellence meets strong risk and reliability practices from design through operations. Education sets the mindset, industry pressure tests it. So, Allison, would you like to share any closing thoughts?
I would say that understand that integrity is a team sport. Define responsibilities clearly, measure what matters, and keep learning, because today's fix becomes tomorrow's standard.
Great. Thank you so much, Allison. We'll just quickly summarize the key takeaways for listeners. So the first one is think systemically. Integrity is end-to-end. Second one, make risk visible and actionable. And invest in communication and learning loops. So thank you everyone for listening. And Allison, thank you very much for sharing your insights.
Thank you, Arti, and good luck, EIT students.
That's a wrap for today's episode. Follow all things engineering and click the link in the description for more insights, tips, and course information.